In this lesson, we're going to talk about imaginary numbers, and I would assume that to you guys, imaginary numbers are probably going to be something new. You might have seen them before, but we call the imaginary unit I, so the lowercase letter I, and it was created by mathematicians to help overcome the problem with equations that didn't have any real number solutions. So we call this imaginary unit the imaginary root, and it's defined as the imaginary unit equaling the square root of -1. So what you guys are going to need to remember is that anytime you see a negative value underneath a square root, it's going to need to be brought out and become the letter I. That's how we operate if we were in a situation where we had a negative number underneath a square root. Because no number you're ever going to multiply together twice is going to give you negative. It just doesn't work that way. So we have the square root of -1 equals I. If you have two of them, I squared, you get the value -1 without the radical. So what this looks like is if you have R, that is a real positive number, then you could have the example, say you had a perfect square of 49, but it turns out that 49 is negative. Well, the negative comes out and becomes I, and then you have to find the square root of 49. So in this case, it would just be 7I. So anytime you see a negative inside a square root, pull it out, becomes the imaginary unit. So based off of that property, because of that square root being -I and what we said up here above, that I squared equals -1, if you guys had in parentheses I times the square root of 3, that whole expression squared, that becomes I squared times the square root of 9. You know that the square root of 9 is 3, and I squared equals -1. So these are your two expressions that you guys are going to want to remember. If you have a pair of i's or I squared, it's going to actually equal the value -1. If you have -1 under the square root and you're trying to take the square root of it, it just becomes a single I. So how do we actually solve an equation with an imaginary solution? So we're saying we have an equation that came from somewhere, and its solution doesn't have a real number value. It's an imaginary solution. So how do we solve for that? So if we look at number 1, here it says 2x squared plus 11 equals -37. You're still going to solve for your x, and we talked about solving with square roots, so we would subtract your 11, get 2x squared equals -48, divide by 2, divide by 2, and get x squared equals -24. Well, to undo the square root and to solve, you would need to take the square root of them both. That will give you your x. But right now, we don't know what the square root of 24 is. But we do know that that negative needs to come out because we can't have a negative underneath the square root. So anytime you see a negative, it becomes I. We now have to simplify the radical. So 24, you could do 6 and 4, 2 and 3, 2 and 2. So you have a pair, 2 that are left. So your answer would be x equals positive or negative, and that 2 comes out with your I. 3 times 2 stays under the radical. And that's your answer. So anytime you see a negative value underneath the square root, it becomes the imaginary unit outside of your square root. It becomes I. You just pull it right out and then you just simplify like you normally would with a radical. So go ahead and try your second one, guys. Number 2. So a complex number, complex is just another word for imaginary. So a complex number means that there has to be an imaginary part in there somewhere. So it's written in standard form when you have a plus bi, and that's when a and b are your real numbers. So the number a is the real part of the complex number, and the bi is the imaginary part. So for it to be in standard form, you need a single constant by itself, and then you need the imaginary part. You need one of each for it to be in standard form. So if b equals 0, then a plus bi is an imaginary number, as long as b does not equal 0, because then there would not be an imaginary part to your number. So if a equals 0 and b does not, so in this case, you would only have the imaginary part. You wouldn't have the constant real part. Then it would just be a pure imaginary number. So two complex numbers, a plus bi and c plus di, are equal if and only if those first two numbers, a and c, are equal to each other, and then the little imaginary parts, b and d, are equal to each other. And just remember, a, c, b, and d are just numbers, just coefficients. So it gives you guys an example. It says, if you had a number, x plus yi, and 5 minus 3i was that number, the real part without the imaginary is 5, and then the y is the part with the imaginary number. So the real part is the horizontal value, and the imaginary part is the vertical value. And we'll talk about that. We're actually going to graph these, and we'll talk about that a little more. So it says, write the expression as a complex number in standard form. So that means a single real part and a single imaginary part together. So let's look at number 5. It says 10 minus 6 plus 7i plus 4i. For right now, when you guys are adding and subtracting, all you really do is treat the i's like terms. So I'm going to simplify it first. I'm going to distribute that negative and make this 10 minus 6 minus 7i plus 4, but then you just combine like terms. So 10 minus 6 gives you 4, and negative 7 plus 4 gives you negative 3i. And that's it. So your imaginary number in standard form with a single imaginary and real part is 4 minus 3i. So go ahead and try the other two, number 3 and number 4. So these next examples also want us to put the expression into a complex number that's in standard form. So again, we have to multiply everything, combine what we can, and make sure that what we're left with is a single imaginary and single real part. So the first thing we want to do is do what your mind is probably telling you to do and distribute that 4i in there. So for right now, just sort of treat them as if they were a variable. So if I have 4i times negative 6, that gives me negative 24i. And I make my eyes a little weird so that they look like eyes and not ones. And then 4i times 1i, remember you can put the 1 there if that helps you. 1i is going to give us 4i squared. So right here, when you see I squared, just like when you see a negative under the square root, it comes out and becomes a single I. When you see I squared, you want to replace that with the value negative 1. So this becomes negative 24i plus 4 times negative 1 now. That I squared has been replaced with the value negative 1 because that's what it's equal to. So this just becomes, okay, well, 4 times negative 1 is negative 4 minus 24i. We now have a real part and an imaginary part, and we're done in standard form. So remember, when you see I squared gets replaced with the value -1, the number -1. So what about number 9? When we were talking about radicals, we said you cannot have a radical or a square root in the bottom of your denominator for it to be in standard form and to be simplified. The same goes for imaginary numbers. You guys can't have an imaginary value in the bottom of your denominator. So we need to rationalize this or simplify this just like we did with the radicals so that that imaginary value is gone. So we still need to multiply by the conjugate. So if the bottom of your denominator is 1 minus 4i, we're going to multiply by 1 plus 4i. Remember, you have to do it on the top and bottom to keep it balanced. So if you guys need to, you can use that box and do 7 and 5i times 1 and 4i. And you'll have to do the bottom as well. 1 minus 4i times 1 plus 4i. Well, on the bottom, since they're conjugates, that middle term goes away. Remember, that just means opposite signs. So you really just multiply the first term. So 1 times 1 is 1. Always going to be minus because it's a negative times a positive. And then whatever 4i times 4i is. So minus 16i squared will become the bottom. On the top, we're going to get 7 plus 20i squared plus 28i plus 5i. So on the top, I'm going to combine my like terms. So I'm going to make this 7 plus 32i, and I'm going to replace that I squared with -1. Same thing on the bottom. I'm going to make this 1 minus 16 times -1. So on the top, this will really become -20. So -20 plus 7 becomes -13. You still have your 32i, and that should be 33. Not 32. 28 plus 5 is 33, not 32. And then -16 times -1 becomes plus. So 1 plus 16 is 17. So -13 plus 33i over 17. So as long as there's no imaginary values in that denominator, you are good to go. You just have to multiply by the conjugate. So just remember, guys, you don't change the sign to the first number. The only sign that gets changed is the one in the middle. So if it were -1 minus 4i, it would not become +1 plus 4i. The -1 stays. It's just that sign in the middle that switches. So when we try to plot these on a coordinate plane, so you guys know how to plot the point 2, 3. You would go right 2 and up 3. What's the same idea when you guys have complex numbers? We said, so like for letter B, -2 plus 4i, the real part is your x and the imaginary part is the y. So if you're trying to graph this, it's as simple as saying if those are the values that associate with each variable or each direction, then this point would be at -2, 4. And that's all there is to it. So point B is at -2, +4. So like for letter C, if there is no imaginary part, or real part, you could write this as 0 plus 3i. Remember, I keep saying fillers are important here. If there's nothing there, it's 0. If that 0 being there helps you, then put it there. So we're not going to go right or left any, and we're going to go up 3. And that will be point C. So go ahead and plot your other 2 points, and I'm going to go down here and look at absolute value of complex numbers. Okay, so the absolute value of a complex number. We said when we were talking about absolute value just with regular values back in Unit 0, that the absolute value is the distance of something, and it's always positive. So the absolute value of a complex number is given in this formula. So we have our absolute value bars around z, so we just call it z. That's our complex number. We find that by taking the distance of our a number squared plus the distance of our imaginary, or our b number squared, and then we take the square root of it. This formula, guys, is really, if you take note, what kind of triangle does this make? A right triangle. You're finding the hypotenuse. This is really just the Pythagorean theorem without doing the algebra to get to the hypotenuse. It solved for the hypotenuse, and it says, okay, plug in the values. But that's all you're doing. You're finding the distance to that point that you plotted from the origin. So this is the distance between the origin and the point on the plane. So that's what you guys are finding when you find the absolute value of something. So like if we find the absolute value of negative 3i, this is really, like we set up above, 0 minus 3i. So if we plug this into our formula, the absolute value, or the distance that point is from the origin, would be the square root of a squared, which is 0, plus b squared, which is negative 3. So you would get 0 plus 9. 0 plus 9 is 9, so the square root of 9 is 3. And it's always positive because it's a distance. And when we graphed it, that point A was 3 units away from the origin. That one was easy because it was right on the axis. But that's all you're doing. You're just finding that distance. Your point is away from the origin. So go ahead and find the absolute value, or the distance, for that complex number negative 4 plus 3i.